Hello dear students. Today we will be discussing two topics, thermocouple and silicon temperature sensor. So first we will move on to thermocouples. So thermocouple as we know is used to measure the temperature in form of electric current or EMF. So these are formed by two dissimilar wires which are connected together to forming two junctions which are insulated from each other, and these junctions will be kept at different temperatures, and depending on the temperature difference you will have some voltages being induced across these wires. So the general working principle of thermocouple is depending on few effects. The first one is Seebeck effect. So this effect simply says that the temperature difference between two junctions due to dissimilar metals induces potential difference between them. So here we have metal A and metal B materials, and these are kept at two junctions. So if you apply a heat at particular junction, you will have a temperature difference between A and B. So because of that, you will have some EMF generated. Now Peltier effect is another effect which says that in the same setup where a thermocouple is formed by two materials, if you apply the voltage across one of these metals, you can have temperature difference felt at the junctions where you are joining these metals. So here if you apply EMF here, you will have a heat absorption here and a heat rejection here. So you will feel the heat at junction B. And you have the third effect, which is known as Thompson effect, which simply says that you will have a heat liberation and heat absorption along the conductor with temperature gradient when a current is flowing through it. So you have a conductor here which carries a current in this particular direction, and during this process of current carrying, you're along with the current carrying process, you are keeping the conductor at different temperatures. This end is kept at low temperature, and this also kept at low temperature, and somewhere in the middle region you are keeping the temperature higher. So there will be a temperature gradient. Temperature will be reducing like in this direction, and the temperature will be reducing in this direction. And here you can see that the current flow is opposite to temperature gradient. Temperature is reducing in this direction and current flow is like this. So here you will have a heat absorption in this particular part of the conductor, and here your temperature is decreasing in this direction, and the current is also flowing in this direction. So here you will have a release of heat in this particular section of the conductor. So this particular effect is known as Thompson effect. Then you have some laws governing the operation of thermocouples. The first one is law of homogeneous metals. Here the thermocouples T1 and T2 are kept at different temperatures, and suppose if metals, and these are due to metals A and B, suppose if any of these metals are kept at different temperatures in between the junctions, say T3 and T4 are the temperatures along the metals. So the EMF generated will be independent of any temperature distribution along the metals, and it will be only depending on the values of T1 and T2. So this is a law of homogeneous metals. And law of intermediate metals says that a new metal, third metal, can be introduced along the metals that is already there without changing the EMF generated, provided that the end of this metal C or the junctions of the metal C are kept at same temperature. So this is your law of intermediate metals. And intermediate temperature law says that you are able to get the net effect of two set of temperatures. That is, if you are having metals A and B kept at junctions 1 and 2, connected at junctions 1 and 2, the EMF generated will be depending on the values of T1 and T2. Now if the same metal A and B is kept at temperatures T2 and T3 at junctions 1 and 2, then the EMF will be proportional to T3 and T2, the difference between T3 and T2. And if you are keeping the same metal at T1 and T3, the EMF will be proportional to the difference between T3 and T1. Now this EMF will be equal to the EMF generated due to the sum of T2 and T1 and T3 and T2. So this is known as law of intermediate metals. Now we construct the thermocouple in such a manner that you are having a hot junction here, and the cold junction is kept far away from the temperature measurement, and from the cold junction you are having wires taken out to measure the voltage. The leads of the thermocouple are encased in this rigid metal sheath, and you are providing some magnesium oxide, and your thermocouple wires are enclosed within the magnesium oxide. in order to prevent vibration which could damage the fine thermocouple wires, as well as to improve the heat transfer capacity between the measuring junction as well as the surrounding region. And the measuring junction is here, the hot junction is here, and you are having the cold junction at this point. And you have different types of thermocouples available depending on the application. Type E is made up of chromal and constant N, which is generally having higher voltage output for a small variation of temperature that you can see from the graph. And J was the one of the thermocouples which were introduced initially. It was having wide application during that period, and it is also used for low temperature applications. And K, R and S are used for high temperature applications. K is made up of chromal and aluminum, and R and S are made up of platinum with variation in percentage of platinum and rhodium as the two metals. These two are used for high temperature application because since platinum is having higher cost, this R and S will be used only for specific applications where you need that much precision or accuracy. And K is generally used for high temperature application. And type T, which is made up of copper and constant, is used for cryogenic application below sub-zero temperatures. And these are the color codings that you can think of related to these thermocouples. Here you can see that type K is being shown here. So here the output wires are in the form of two cables, red and yellow. So this is a type K kind of temperature sensor. So this is your hot junction, and this will be your cold junction. Some of the advantages of thermocouple is that they are cheaper than other measuring devices. They are having fast response time and have wide range of operation. It can be operated up to 4000 degrees Celsius if they are properly cooled, and it can be made from fine wires as well as heavy gauge wires. And they suffer from the disadvantage that they have low accuracy when compared to RTDs in comparison, and recalibration is a difficult process, and reference junction temperature compensation is required. So your reference junction is the cold junction, and initially when it was introduced in 1800s, the process was 1800 period year. And the process was that used to keep the cold junction in ice bath, and used to measure the temperature at the used to provide temperature at the hot junction. You always kept this cold junction as at ice bath. So some reference tables were introduced based on this ice bath temperature. Now, but currently during our operation, you are not keeping the cold junction at 0 degree or less than that, but rather it will be at the ambient temperature, and you will be providing the heat to the hot junction or temperature to the hot junction. So in order to compare the results with the table which is already there, the temperature table which is already there, you are making some compensation, assuming that, or compensation to negate that increase in temperature from 0 degree or ice bath temperature, ice cool temperature to the ambient temperature at the cold junction. So that compensation is in terms of voltage difference, some voltage changes which will be introduced in our signal conditioning, introduced by the signal conditioning circuits, so that your EMF will be or the output EMF will be in such a manner that your cold junction is assumed to be at ice bath temperature, and the difference temperature will be the actual temperature that is at the hot junction. So that is your cold junction compensation or reference junction compensation, which is required in terms of thermocouples. And some of the applications are that they are used in iron and steel industries to monitor the temperature in electric furnaces. They are having high temperatures, so we are using BSRK type of thermocouples. They are also used to measure the intensity of incident radiation, solar radiation, in terms of thermopile radiation sensor. They are also used in thermostats in our general applications like in air conditioners, and they are also used for finding out the temperature in switchgear equipments like circuit breakers, while testing to find out the current carrying capacity, whether the temperature is increasing or not. It is also used in chemical production as well as petroleum refinery plants to measure and monitor the temperature at different stages of the plant. Now we'll move on to silicon temperature sensors. These are advanced devices which comes in the form of integrated circuits. So you have a single IC which integrates the entire temperature sensor as well as other signal conditioning circuits also. Normal IC operating temperature is in this particular temperature range, and they can also be integrated with other electronic chip boards such as microcontrollers, signal processing circuits, and analog to digital converters. Even a single chip can be formed by integrating all these things together: microcontrollers, signal processing and conditioning circuits, as well as converters, along with the temperature sensor, to form a single IC, which can be a full-fledged IC which can be directly connected to the electronic circuit board. So this is used. These diodes can be used in temperature sensing due to their strong temperature dependence of forward bias voltage drop. They are having low cost. They exhibit a very simple voltage relationship or wide range of temperature. They can be integrated with the electronic circuit board. They measure the temperature in terms of absolute values. They exhibit a good sensitivity as well as accuracy, and their performance deterioration due to self-heating. The self-heating effect is there existing diodes also, so that can be reduced by operating the silicon diodes at low currents. Now LM35 is one of the commonly used thermo diode that you can think of. It is calibrated directly in degrees Celsius, and it is having a temperature range of almost 200 degrees, and it is can be used for remote applications as well, and as having low cost, and it operates at a voltage range of 4 to 20 volts, and it is having low self-heating. And this is the image for LM35, which is similar to a diode and can be directly used to sense the temperature. The output is in terms of voltage, so you can get the output in terms of millivolts, in terms of voltage or millivolt, and that millivolt voltage can be amplified and can be used for further signal conditioning processes. And this is a voltage temperature relationship that exists in silicon as well as gallium, aluminum, arsenic type of material. Here you can see that you have a linear range of operation or linear relationship in this range. Some say 50 degree up to 500 degrees you have linear temperature range, and this is being operated in constant current mode. So constant current mode is one of the commonly used current operating modes of these diodes. So below this particular range, say from 30 to 40 degrees, you have a sharp increase in voltage, and for higher temperatures like 600 Kelvin, your relationship will saturate. The voltage change will not be there, and the voltage will be saturated. So you have a linear operating range in this particular temperature gap or temperature range, which is being used for practical applications. And the constant current mode is the most commonly used one, and whatever we have explained, you have linear range, and then you have at the ends you have a different operation. And these are used for temperature compensation, for stress, pH and pressure sensors. It can also be used for low temperature as well as high temperature measurements. It is also used in gas sensing, IC and chip temperature monitoring, especially in electronic devices, flow sensing as well as thermal conductivity of gases. It is also used for sensing other parameters like infrared, liquid level sensing as well as humidity sensing. So it's a wide range of application which is being utilized. And this is one of the operation of a thermodiode. This is a micrograph of a thermodiode, which is a zoomed version. So here you can see that the thermodiodes, which is used to measure the temperature. So this will be part of the circuit board. Here you can see that the connections are also provided. So this is a part of the circuit board, PCB printed circuit board that you have, and you can use this thermodiodes to this can be incorporated in your circuit board, or this can be used in terms of individual ICs also. Now we'll have a quick comparison between what we have learned. So we have learned 4 types of temperature sensors: thermistor, RTD, thermocouple and semiconductor based silicon temperature sensor. So the widest range is provided by thermocouple operating range. It is having high accuracy and repeatability, but it needs cold junction compensation, as we have already seen, and it is having low voltage output in terms of millivolts. And in case of semiconductor device, we are having voltage output in terms of volts, but the sensitivity is in terms of millivolts. you are getting the voltage output in terms of volts. And all the other three except thermocouple requires excitation, external voltage source. And RTD is having temperature range in this sense. Thermistor is having low temperature range, and semiconductor is having a better range when compared to thermistor. And RTD is having fair linear property, and semiconductor is also having a good linear and accurate property. And RTD is the cheapest one, and thermistor is having highest sensitivity, and thermocouple is having the widest range of operation. So this is the comparison that you can think of. So thank you so much.